So there's two things. You have two stars. Oh, this is gonna work out well. That's not a very good star. I should have just done a circle. So yeah, all stars are perfect circles with these nice little rays coming out, right? Okay, so you have star A, you have star B, which is red, and one is blue. And they're basically like, why would one star appear brighter than the other?
They say the reddish one is brighter than the blue.
Oh, they said the reddish one is brighter than the blue one. So if you look at, let me actually show you one of these charts.
The red one probably closer and a lot bigger because it might be going supernova.
Well, one of the things I want to show you real quick. No, it's not going supernova. It's actually, if it's red, it could be dying. It's definitely going to be cooler than the blue star because blue is hotter. But hotter doesn't always mean brighter. It usually does.
Is this a real image?
Huh? No,
I think it's because
I don't think so.
So
Fake
Well, it's
news.
pixelated,
It's
so it
really
could be
hot,
like
right?
zoomed in on top.
I mean, technically, maybe it could. I don't know
I
if
think
it's
that's what
really.
he's talking
I
about.
don't think it is. But
It looks cool though.
Here we go. So this was one of the questions I asked you about in the. Let me unfreeze this. In the assignment yesterday, and kind of talked about. So this is the Hertzsprung-Russell diagram, and this shows you. First off, this chart has 4 different axes on it, and y'all can see this at home. So spectral class is just how we classify them. On the left, you have luminosity, which is brightness. On the right, you have absolute magnitude, which is also brightness. And then on the bottom, you have surface temperature. So that's how hot it is. So the blue stuff is hotter than the yellow and the red stuff. The red stuff's going to be cooler. And basically, they're like you have a red star and a blue star, and the red one appears brighter. So first off, if it's a red giant, it could appear brighter than some of the smaller blue ones. But more than likely, let's just pretend that it's a regular red star down here on this end. How is it going to be brighter where the blue ones are the brightest, the red ones are kind of the least bright? That could be that it's just a lot closer to you. Because they're not really talking about absolute magnitude. They're just saying you're looking up into the sky and you see a red star and you see a blue star and the red one's closer. So generally what that's going to mean is if this is your drawing of your red and blue star, let me grab my black marker, you're going to be looking from over here. I don't know how to draw continents. This is going to be bad, but you're going to be looking from over here. You're a giant standing on the earth. But the red star's going to be much, much closer than the blue star. And so even though its absolute magnitude is lower, can everybody see that? Yeah, you can see that. Even though its absolute magnitude is smaller, it's not as bright if you were the same distance away. You're probably not the same distance away, and so the red one being closer is going to look brighter than the blue one. Also, it could be a red giant. If it's a red giant and they're about the same distance, it could look brighter than the blue one, depending on how big the blue star is. But yeah, that's a Hertzsprung-Russell diagram. This is actually a really nice diagram, and we talked about this yesterday because you asked about the sun. The sun is just really average. It's not too bright, not too dim. It's nice and yellow. We're in the Goldilocks zone where we're not too close to it, not too far away. And so we have a pretty average basic star.
How hot are the supergiants?
The supergiants, so our sun is about 1 luminosity. The sun equals 1, so it's exactly 1 luminosity. The temperature of our sun is probably going to be, I'm guessing, around 8,000 degrees on the surface, and that's Kelvin, where your supergiants range from like 10,000 all the way up to 20,000 degrees Celsius, or Kelvin, not Celsius.
That yellow at the top.
Oh, that supergiant? My bad. Yeah, I thought you were talking about the blue ones. These are going to be, it's giant, but it doesn't really burn any hotter. And so the color really matches up to the temperature.
Why is that one so big?
It's just a lot bigger. It's a bigger star, and the reason these are so big generally with your red giants and your supergiants is because they've burned out a lot of their fuel, and so at this point, the gravity isn't. How do I explain this properly? The gravity isn't matching the outward expansion of their energy release, and so that's why they get bigger. So when we talk about the sun going into a red giant phase and the Earth getting destroyed, that's what's going to happen. As it starts to die, the sun that's about this size is going to expand to about that size.
So does it go from like the sun is now to a red giant to a super giant, or does it just go?
No, and actually they have a death cycle for this. Let me see if I can find it real quick. After the red giant, it will probably go and become a white dwarf. Only stars bigger than our sun could possibly become a supergiant, and the really big ones end up going supernova. Ours will not go supernova. It will get big into a red giant, and then it'll collapse down really, really small into a white dwarf. Let me see if they have that cycle real quick. It might be. I don't think it's on the next page because the next page is
If our
galaxies.
sun was a super giant, how far would it expand?
That's Jupiter, right?
How big would it?
So here we go. This picture answers your question. Not for a supergiant, but for a red giant. Here's the sun currently. When it becomes a red giant, it's going to expand out. It's going to take out Mercury, then Venus, and then Earth. And it looks like it'll probably stop just beyond Earth. So it probably will not take out Mars. Mars would probably be somewhere out here.
So we just made the cut.
Yeah, we're just missed the cut, I guess, because we'll be gone. But yeah, it just depends on which way you look at it. But yeah, it will take out Earth and probably not too many other planets.
But do you think as the sun, as it starts getting bigger, all the planets will start like sucking into it more? Like would it start getting more gravity?
I don't think so because the size expands, but it doesn't have any more matter inside of it, so the gravity will probably stay the same.
Gravity's what's keeping it small.
Yeah, the gravity currently is what's keeping it small, but I don't think it'll get more gravity when it expands into a red giant.
So how much bigger is a super giant?
Supergiants, well, it depends on the star because they're all going to be a little bit different. But generally, I think to get to a supergiant, you have to be maybe like 8 times bigger than the sun or bigger than that. So maybe 8 times bigger than that. Now that is,
Then the red giant?
yeah, that's volume size. And so, it's not like 8 times further out.
Right.
But let me see if I can find a comparison for that. First, let me see. Do they show the life cycle of when a star dies? Death of a star. It should be right under here. Black hole. Hold on. Let me do it this way because I know it's in this. Come on. Quick access. PowerPoints. Maybe I should just lecture to y'all from these PowerPoints instead of using Discovery Education. Our solar system. I think it's going to be beyond our solar system. Is it opening? Open. Yes. So let me come down here. Oh, it's really not in here. That's disappointing. It's going to be in our solar system. Oh, come on. Okay, so come down. Stars, planets. Is it not going to be in here? It's got to be in one of them. How's it not? Oh, this is disappointing. Does this one have all the... What's up? There's the Hertzsprung-Russell diagram. Here it is. Okay, so here is like the life cycle of our star. So it starts from a cloud of gas and dust. It forms into a protostar early on. This is like a baby star. Gravity takes over and you get fusion. It enters into the main sequence where it spends like 90% of its life. It will stay here for a very long time. Once the fuel starts to burn out, it expands into the red giant stage. If it's big enough, it will become a supergiant, but it'll probably just be around this size, red giant. It goes into a variable stage where, some of this stuff we're still kind of learning as we watch it out in space. But it'll change size a little bit, and then eventually the fusion that happens that pushes it outward will stop altogether or almost stop, and gravity will take back over, and it will go down into a white dwarf stage, which is smaller than the star. Your supergiants, the really big ones, will explode into a planetary nebula or a supernova. But the white dwarfs will basically be really, really small, really, really dense and compact. Here, let me go to the next one. Hold on. Yes, this shows you the three different sizes. So for small stars, medium-sized stars, which are like our sun, and then large stars, this is what they do. So for the small one, you go from nebula to protostar to main sequence, which is a tiny little red one instead of a yellow one like we have. And then it goes to a white dwarf. For ours, you go from your yellow sun like we have it now, it expands into a normal red giant, then it explodes into a planetary nebula, and that contracts down into a white dwarf. For the really big ones, it goes from a main sequence, which is blue instead of yellow. It goes into your red supergiant and then explodes in a supernova and can either convert into a neutron star or a black hole, depending on how large it is or how much energy it has. And so these are the three different life cycles of a star. And they should have this in Discovery Education.
Do we know where any super giants are?
Yeah. I think Betelgeuse. Well, red supergiants right now. I might have to look it up and see. But we know many really, really large main sequence stars that will eventually go supernova. One of the biggest ones is Betelgeuse. Like the movie character Beetlejuice, but maybe spelled different. But yeah.
What was that actor talking about that one day where you can look at constellations and stuff?
Yeah.
What are you talking about?
Where you can like
You
hold
said
your
when
like
it's
on your
sky,
phone
when
and
it's
like.
sky.
Oh yeah. The one I have, there's lots of different ones. The one I have is called Sky Safari.
Not download it.
If you want to, go for it.
Like I was gonna
Don't be
do
messing
it,
around on
about
your
it, and then I forgot about it, and I got on there yesterday to look for it.
Yeah, it's called Sky Safari, and it has kind of like a purple icon with people standing there, and they're kind of looking at the moon. But I'm pretty sure it's free. I don't pay for apps, so it has to be free. I don't even have like a card in my phone, so. No, it's not. Sky Safari? No way.
With two people looking up at the moon.
Hold on.
The moon's like
$2.99.
crescent moon.
What are y'all? Y'all have iPhones or something?
Yeah.
Hold on, let me see. There's no way I paid money for that. Really, like almost any of them would work.
No, that one costs money too. It just doesn't tell you until you get in there.
Really?
Yeah, the Stargazer app. I downloaded that one yesterday. And like whenever you get in there to set it up, it's like
It's like those hell apps.
Mine had to have been free.
yeah.
Maybe I did. But,
On Android, it's free.
On Android, it's free.
boom. See, I told you it was free. Get a free one. There's nothing super special about this, but just get one that has good reviews.
This one has 3.6.
Maybe look up like Sky Map or Star Map, and you can find something. Yeah, I'll survive. I might have some internal bleeding, but Okay. So if you have any questions, please send me an email or let me know. There's just 2 questions on the assignment today. Make sure you answer all the little parts of the questions, because there's several different things. So if you have questions, let me know and send me an email and I'll get back to you. Thank you.